Imagine you are looking at a stunning, perfectly smooth photograph of the universe. The galaxies are sweeping across this dark void, and the math just seems to glide effortlessly along these continuous curves.
Right. It's that classic beautiful picture we all have in our heads.
Yeah, exactly. But what if when you zoom in close enough, that smoothness just completely shatters, like it breaks into sharp, discrete, blocky pixels? What if the fundamental math we use to describe reality is, well, exactly the same, just a smooth illusion that's painting over a deeply pixelated universe?
It's a really profound shift in perspective, honestly, because, we are just so used to the comfort of continuous fields in physics.
Right.
This whole idea that between any 2 points in space or, any two moments in time, there are infinitely smaller points seamlessly connected. It's literally how we've built almost all of our models for the last century.
Well, okay, let's unpack this because our mission for today's deep dive is going to totally challenge that entire foundation.
Hmm.
We are looking at a paper by James R. Gibson, and it's called Constrained Extremization in W-Field Calculus.
That is a mouthful of a title for sure.
Oh, absolutely it is.
Yeah.
But the goal here is to figure out how this paper completely reformulates a classic quantum physics problem. Specifically, how a system finds its optimal, most stable state. We're moving away from that smooth, continuous math into this discrete, what they call Gibsonian framework. And I know that sounds incredibly heavy, but I promise you, it is fundamentally about how the universe actually, computes reality.
Yeah, and to even begin talking about how the universe computes an optimum state, we really have to first talk about the physical substrate it's computing on.
Right, the actual hardware.
Exactly, because traditionally, if you want to find an optimal state in quantum mechanics, say, the lowest energy state of a system, you use something called Hilbert space variational analysis.
Wait, okay, let me pause you right there. Before we get into all the Gibsonian stuff, what does that actually mean in plain English? Like Hilbert space variational analysis.
Fair question. Think of it as a mathematical landscape. In traditional physics, we just assume the background of reality is this continuous, infinitely divisible void.
Okay.
So when physicists look for an optimum, they are basically trying to find the perfect peak or valley in that really smooth mathematical landscape, subject to some constraint. And to do that, they rely on continuum-derived equations, things like the Euler-Lagrange equations.
Right, and for those of us who don't, dream in calculus every night, Euler-Lagrange is basically the math of drawing those perfectly smooth curves, right? It's like finding the absolute path of least resistance across a continuous surface.
That is a great way to visualize it, actually. It assumes the universe allows you to just glide smoothly from point A to point B. But Gibson's ontology argues that observable physics isn't a continuous background at all.
Not even a little bit.
No, the reality we see is actually the rendered output from local token exchanges happening on a discrete tetrahedral lattice.
A tetrahedral lattice.
Right, so picture a massive three-dimensional grid made entirely of tiny pyramids. Nothing is smooth. Everything is just local units passing these discrete, indivisible tokens back and forth.
Okay, so to try and ground this, is traditional quantum math sort of like drawing a theoretical line on a map to plan a road trip? Like the map says, go from New York to LA, and your pen just effortlessly glides over mountains and rivers, no problem.
Yeah, exactly.
But then this Gibsonian framework, it forces you to actually get in the car and drive the route block by block, dealing with, actual traffic lights and physical detours.
That captures the surface of it, yeah. But let's actually take that analogy a bit deeper. When you are drawing the line on a map, you're just doing algebra. You don't care if there's an uncrossable canyon in the way, right? Because your pen isn't bound by the physical terrain.
Right, the pen just draws over it.
Exactly. But when you are driving the car, you are bound by physical realizability. You can only move forward if you have the gas in your tank and the road is actually paved in front of you. And this is where Gibson introduces something called W-field calculus to handle the physical driving.
So W-field calculus isn't just like a new way to draw the map.
Far from it. Physicists create numerical approximations of continuous equations all the time just to make the math easier. This is not that.
Okay.
W-field calculus is an actual ontological base layer. It uses token-weighted derivatives, which basically means the math tracks the local congestion of reality.
Oh, wow.
You can't just mathematically glide over a point in space. The system has to possess the actual discrete tokens to move through it. Reality, at its absolute lowest level, is governed by counting constraints.
Okay, I'm really trying to visualize this. If reality operates like this block-by-block token exchange rather than a smooth line, what are the actual rules for moving from one block to the next? Because on my road trip, I can't just blow through a red light just because I want to get to LA faster. The universe has to have its own traffic laws, right?
Oh, it does, and they are incredibly strict. This actually brings us to what the paper calls the full complement rule and T-transfer dynamics.
Okay.
To understand this, you really have to separate configuration space from rendered space.
Meaning the hidden gears inside the clock versus the face of the clock that we actually look at.
That is a brilliant comparison, yes. The W field operates in the configuration space, those hidden gears. On this hidden grid, you have nodes called S units.
Oh, S units, got it.
And these S units are constantly trying to advance in configuration time. To take one step forward in time, an S unit has to execute a T transfer. But it can only do that if it receives a sufficient local complement of T particles from its immediate neighbors.
Hold on, S units, T particles. I'm already losing the thread a bit here. What exactly are these things?
Sure, okay. Think of the S unit as a specific toll booth on your road trip, and the T particles are the actual coins needed to pay the toll.
Okay, that makes sense.
The toll booth cannot open the gate, meaning it cannot advance forward in time unless it receives the exact right number of coins from the surrounding traffic. It has a strict, uncompromising incoming token budget.
Wait, let me make sure I'm hearing you correctly here.
Mhm.
If an S unit, like a localized piece of the universe, has a token deficit, meaning it just doesn't get the coins it needs from its neighbors, does it just freeze? Does time literally stall for that specific microfraction of reality?
That is the necessary implication, yes. It simply cannot advance.
That is wild.
It is, and this is what makes physical realizability a strict local support condition. If you are listening to this and trying to picture what a local support condition means, imagine a marching band.
Okay, a marching band.
The band can only step forward if every single member has room to put their foot down. If one person is blocked, the whole formation either halts or it breaks completely.
Right. So bringing this back to the traditional quantum physics we talked about earlier.
Right. So in that smooth, continuous Hilbert space math, a proposed state might work out perfectly on a theoretical chalkboard. The algebra says, yes, this is the optimal energy state.
The math checks out.
Exactly. But if you actually try to run that state on the discrete tetrahedral lattice and it violates the full complement budget, like if it demands tokens that physically aren't there, it fails completely. The paper calls a state like this an algebraic ghost.
An algebraic ghost. What a term. I mean, it's a mathematical hallucination.
Mm-hmm.
The classical physicist is looking at the chalkboard, totally thrilled that they solved the universe. But the universe itself is basically saying, well, I don't have the hardware budget to run your program.
It really highlights a massive blind spot in continuous math. If a state doesn't have local support, it just doesn't matter how beautiful the global equation is.
Wow. Okay, so we know that movement and time require this rigid token budget. But what does a physical state actually look like when it's built out of these localized traded tokens? Like if I have a particle or a system of particles, it can't just be a simple point on a graph if it has all these complex toll booths and token exchanges going on underneath it.
Yeah, and you're touching on one of the paper's heaviest critiques of classical physics here. The paper totally rejects what it calls scalar caricatures.
Scalar caricatures, like turning a complex reality into a flat cartoon.
Essentially, yes, because a scalar is just a single magnitude, a single number. Traditional physics often reduces a quantum state down to just its occupancy, the simple amplitude, or basically how much stuff is at a given point.
Right.
Gibson argues this is a huge caricature. In the discrete framework, every candidate state is what he calls a multi-channel accumulation object. It isn't just a point. It is a deeply structured accumulation of discrete tokens that have all stacked up over time.
Okay, I'm trying to wrap my head around a multi-channel accumulation object. It sounds like instead of just, a single marble sitting on a table, we are talking about a highly complex architectural structure.
Let's look at the hidden architecture the paper describes. When Gibson analyzes a local state, he isn't just looking at the sheer volume of tokens. He tracks multiple hidden layers of structural integrity.
Okay, what kind of layers?
Well, there is the packing density, which measures how concentrated the modes are. Then there is the phase cohesion, which looks at how strongly a local site locks into its surrounding neighborhood. And perhaps most importantly, there is something called shear debt, or constraint frustration.
Wait, shear debt. That sounds like an engineering term. I'm imagining, well, actually, let me see if this works. Is this like looking at a Jenga tower?
Oh, that's good. Take that analogy further. How does traditional physics look at the Jenga tower versus Gibsonian physics?
Okay, so traditional physics, that scalar caricature we talked about, it looks at the Jenga tower and just measures its height. right? It says, hey, the tower is 3 feet tall. That's the occupancy. Everything looks great.
Right.
But the Gibsonian math is looking at the shear debt. It's noticing that I've pulled out almost all the pieces at the bottom. The center of gravity is horribly skewed, and the internal stress is just screaming. So the traditional math thinks the tower is totally stable because the height hasn't changed yet. But Gibsonian math knows the entire thing is fundamentally unstable.
That is a phenomenal way to understand it, yes. The shear debt is the accumulated mismatch between what the system is trying to do and what the local hardware actually permits. If we connect this to the bigger picture, it completely redefines what an optimum state even is.
Because if the shear debt is too high, your optimal state is just going to violently collapse the very moment the universe tries to run the next update cycle.
Yes. In classical physics, an optimum is often just an algebraic stationary point. The mathematical derivative hits zero, it flattens out, so we declare, we found the stable valley.
Right, job done.
But Gibson is arguing that an optimum cannot be judged merely by hitting a mathematical flatline. The visible object is only one projection of its deeper state. A rendered extremum has to be a stable, discrete accumulation object.
Which means?
It must be judged by whether its hidden structural organization, like its shear debt, its cohesion remains supportable under actual stress.
So, okay, we've established that reality is this structurally complex Jenga tower constrained by a very strict token budget. The million-dollar question then is, how do we actually find the mathematical peak or the stable valley without the whole thing collapsing? Like if the old continuous math is hallucinating, what does the new math do?
This brings us to the core technical achievement of the paper. It's called the Gibsonian resonant constrained extremum principle. Instead of just solving one simple equation, Gibson lays out a multifaceted stress test. For a state to be a true extremum, it actually has to satisfy 5 different conditions simultaneously.
Yeah, I read through that section, and it is intense. It feels less like solving an equation and more like, I don't know, passing a physical inspection.
It really is an inspection. First, the state still has to look mathematically like an optimum at the surface level, what the paper calls W-objective extremality. The global constraints still have to balance, and the probabilities have to normalize.
So far, that kind of mirrors the classical goals, right?
Exactly. But then the Gibsonian framework adds the hardware checks.
The toll booths and the Jenga tower stress.
Precisely. Every single active site must pass the full complement admissibility test, meaning absolutely 0 token deficits allowed. And the multi-channel stability must hold, meaning the optimization failure functional, which tracks that shear debt you mentioned, must remain sub-threshold. If the internal stress gets too high anywhere, the solution is thrown out.
Okay, here is where things started getting incredibly weird for me when I was reading the source material. The paper introduces this concept of weak versus strong constraints, and it uses this really minimal 2-mode example to do it.
Oh, yes, the 2-mode system.
It completely broke my brain because it shows just how easily classical physics can get tricked. Can you walk us through that 2-mode example?
Sure, let's break it down. Imagine a very simple universe that only has 2 modes, or 2 sites. In traditional math, you might have a global constraint on your system that says the total output must equal 0.
Okay, simple enough. The total has to be 0.
So let's say site 1 registers a positive 1, and site 2 registers a negative 1. Positive 1 plus negative 1 equals 0. The math works. The global constraint is completely satisfied.
Right.
In classical Hilbert space, you pack up your bags, publish your paper, and collect your Nobel Prize.
Because globally, the average is perfectly balanced.
Exactly. But Gibson calls that a weak constraint. It only vanishes at the rendered surface, at the global accumulation level. A strong constraint, which is what the physical Gibsonian substrate actually demands, requires that the math must equal 0 locally at every single active substrate site.
Which totally ruins the classical solution because, site 1 is a positive 1. That is definitively not 0. And site 2 is a negative 1, also not 0. So locally, down in the actual dirt of the physical hardware, the constraint is just failing everywhere.
You see the problem now. The weak constraint is a mathematical illusion that only exists if you zoom out far enough to blur the pixels. Furthermore, let's tie this back to the tokens we talked about.
Okay.
What if site 1 in that example doesn't just equal positive 1, but it is actually complement deficient? What if it doesn't even have the token budget to exist in the first place?
Oh, the classical equation wouldn't even know, would it? It's completely blind to the tokens.
It is entirely blind to it. It just sees the numeric value of +1 and -1, calculates 0, and declares the state optimal and stable. But in the Gibsonian framework, because site 1 lacks its token complement, the configuration is an algebraic ghost. It is completely inadmissible, regardless of what the weak global constraint says.
This is deeply unsettling. I mean, are you saying that traditional physics is regularly hallucinating optimal solutions? That we are basically filling textbooks with states that average out to zero globally, but if you actually tried to instantiate them in our real universe, they would violently break the rules of the local physical substrate?
The paper actually proves this mathematically. It demonstrates that the classical constrained equation, the one standard physics relies on, is merely a shadow limit of the true Gibsonian system.
A shadow limit,
Yeah.
meaning it's just a pale, degraded reflection of the actual math.
Yes. The classical equations only work if you magically ignore lattice coupling. They only work if you assume there are never any complement deficits, and if you assume local failure and shear debt simply don't exist. It basically demands that the universe has an infinite budget and perfect structural integrity everywhere, instantaneously.
Which, based on everything we've talked about, is a massive, completely unrealistic assumption.
It is an assumption born out of mathematical convenience, not physical reality. The Gibsonian formalism does contain the ordinary Hilbert space result, but only as a highly idealized special case. In the pixelated grit of actual reality, that special case almost never holds true.
Wow. So if you were listening to this, you might be wondering, okay, this is a fascinating critique of quantum mechanics, but why does this matter for the future of technology? Why should I care about discrete optimization flows? Because obviously, if you're a quantum physicist, your hair is on fire right now. But what is the practical application of viewing the universe this way?
The most immediate and profound application is in something the paper refers to as world computer architectures.
World computer architectures. Meaning, if the universe is essentially functioning as a discrete computer, our own computational architectures need to mimic it if they want to simulate reality accurately.
Exactly. Or even if we just want to optimize complex systems efficiently, because currently, think about how we solve a massive constraint problem in computer science or engineering.
We plug it into a supercomputer and wait for an answer.
Right. And mathematically, the computer is solving an eigenproblem.
Wait, for those of us who don't spend our weekends doing linear algebra, when you say solving an eigenproblem, you just mean finding that single, perfectly balanced mathematical state, right? Like the system computes everything all at once, finds the stationary peak, gives you the coordinate, and says done.
Yes, it solves it once, in a single pass, and assumes the solution is globally stable. But the W-field evolution law suggests a totally different dynamic optimization protocol. In a Gibsonian world computer architecture, you don't solve it once. You iterate token-mediated updates sequentially.
So it's an active, continuously running process.
It has to be. After every single update cycle, every time the tokens move, the system evaluates the actual physical geometry. Is the strong constraint still satisfied locally? Are all active sites still fully token admissible? Is the shear debt still subthreshold?
And if a complement deficit pops up during one of these micro updates,
The configuration is rejected or redistributed immediately. It shifts our entire concept of optimization. We are no longer trying to solve an algebra equation on a piece of paper. Optimization becomes the active maintenance of parity, support, and hardware lock through every single sequential update cycle.
hardware lock. I love that. It gives optimization of physical logic. I'm thinking about this in terms of building a skyscraper.
Okay, go on.
The traditional method is designing a beautiful building on paper, proving that the math works, building it, and then walking away just hoping the wind doesn't knock it down.
Right.
But the Gibsonian method is like having a living building where you have to monitor the physical stress on every single bolt and beam every second of every day. And if one bolt suddenly gets too much shear debt, the system redistributes the structural load instantly before the building can collapse.
That analogy is spot on. The Gibsonian framework integrates the mathematical optimization entirely with the physical realizability at the hardware layer. It's a much more grounded, realistic notion of what a stable optimum actually is. It demands that the solution survives the friction of reality.
It fundamentally changes our entire relationship with the concept of a solution. Okay, we've covered a massive amount of conceptual ground today. Let's do a quick recap to pull all these threads together. We started with the classical view of quantum math, the smooth, continuous map drawing approach, where finding an optimum just means solving a global algebraic equation and gliding over the details.
And we contrasted that with the Gibsonian ontology, where the universe is actually a discrete, deeply pixelated tetrahedral grid completely driven by local token exchanges.
Right. And we learned that to find a true optimal state in that pixelated reality, you cannot just rely on weak global averages. You have to maintain a strict local token budget, ensuring every S unit has its t-particles. That's the full complement rule. You have to treat states as multi-channel accumulation objects, tracking their hidden internal stresses and watching out for sheer debt before the Jenga tower falls. And finally, you have to ensure that your local hardware logic doesn't fail cycle by cycle.
Because the moment that local hardware fails, your beautifully balanced global equation is completely meaningless. Your solution isn't real. It is just an algebraic ghost.
So the next time you hear about a revolutionary mathematical model solving a massive real-world constraint, whether that model is in physics, economics, or computer science, you should ask yourself a very Gibsonian question. Is this solution just a weak algebraic average that balances out globally? Or is it actually realizable on the ground, block by block, token by token, stress test by stress test?
Yeah, when we ignore the substrate, we ignore the very mechanisms that allow a system to exist in the first place. A map is completely useless if it routes you over a bridge that hasn't been built yet.
Which leaves us with a pretty wild, unsettling thought to chew on as we wrap up. Gibson's paper proves mathematically that if a proposed solution violates the full complement rule, it simply cannot physically render. It remains an algebraic ghost. So, looking back over the last 100 years of physics, how much of what we currently accept as fundamental truth, the grand models we teach in universities, the continuous equations we rely on to describe the cosmos, might just be a vast, complicated gallery of algebraic ghosts, beautifully drawn on a chalkboard, but entirely incapable of rendering in the physical, pixelated substrate of our actual universe?
It is definitely a sobering thought. If we are spending all our time drawing perfectly smooth lines across a pixelated reality, we might be entirely missing the actual roads.
The ultimate scalar caricature. You can draw a straight line right over a mountain on your paper map, but when you're actually in the car, you still have to drive the physical grade. Thanks for coming along for the deep dive today. We will see you on the next one.